This is the 5th video on rotation, rotational energy. Here we have an object that is moving, but it does not move anywhere. It stays put, but it is moving. You can see that it has a kinetic energy. This particular example has rotational kinetic energy. Because it normally stays in one place and it's rotating, and that's where it gets its kinetic energy from, because it's moving. So if we look at rotational kinetic energy, has kinetic energy due to its rotation. It is given by this equation. If we compare that with the linear one, which equals a half mv squared, you will see that we've changed the m to I and v to omega, just like we've done in a number of the other equations linked to rotation. So right, let's watch this and consider a ball rolling down a ramp. Now, if we actually did this experiment, we could measure the gravitational potential energy at the top, which we'd say is mgh. We could also measure the kinetic energy at the bottom, which equals a half mv squared. And if we actually did this experiment, we would find that mgh is much, much bigger than a half mv squared. Now, we've always considered the conservation of energy before, and we've equated those two. And it's so much bigger, we couldn't explain it for work done against friction or anything like that. The energy has to be going somewhere else. But because this ball is rolling, as well as having this linear kinetic energy, it also has a rotational kinetic energy, which is a half I omega squared. So it has that rotational kinetic energy as well. So what we find is that the mgh actually goes to the half mv squared plus the half I omega squared. Or we can say that the gravitational potential energy goes to the kinetic energy for the linear plus the kinetic energy for the rotational. So we've got that there. So it happens that the gravitational potential at the top, at the bottom, it goes to kinetic energy, but the two forms of kinetic energy. If we look at the summary here, we look at the ball rolling down the slope again, and the equations that I mentioned on the previous slide. The other thing we need to remember is that V equals R omega. So there's a direct link between the omega and the V in the two equations. So if we've got objects rolling down a ramp, now these objects, I know this is an animation, but this would actually happen in reality, have the same mass and the same diameter. But they all get to the bottom of the slope at different times. And good question would be why? They all start with the same gravitational potential energy, and at the bottom it must have all been converted to kinetic energy. But why do they get there at different times? Same mass, same diameter. But what we need to remember is that as they come down, the proportion between the rotational kinetic energy and the linear kinetic energy is different. Let's look at the inertias of these different objects. What we have there is a solid cylinder, which is this one here. We have a solid sphere. We have a hollow sphere. And a hoop, a thin-walled hoop. And if we look at those, and these are the values of the inertia and how to work them out, remember R is the same for all of them because we defined that. So because R is the same, the largest one is here. That is the largest. The second largest is this one. Third largest is this one. And the least, if you like, is the fourth one here, of the four we're considering. As a matter of interest, you can calculate inertia of odd-shaped objects like the teapot here by using the sum of mr squared. And if we considered it made up of lots of little bits of mass, we could add them together. And obviously those of you doing calculus will have recognised that with a number of shapes you can describe in calculus, you could actually work out the mr squared in calculus. So we've got the four shapes, four different inertias for each of them. So let's go back to what we saw before. Here we are. We have got our four objects rolling down the same ramp. Remember that they have the same mass and they have the same radius or diameter. So we've got them going down the slope. Let's just consider the two cylinders. Well, the cylinder, if you like, and the hoop for now. So if we consider the cylinder and the hoop, we've got a solid cylinder and we've got a hollow cylinder or a hoop. So EP is the same for both. So we know that EP is going to equal EK linear plus EK rotational. So we've got the MGH is going to equal EK linear, which is a half mv squared, plus EK rotational, which is a half I omega squared. Now omega is linked to V, as we said, V equals R omega. So if we put V in instead of the omega and rearrange, we get MGH equals a half mv squared plus a half I, and putting V over R instead of omega, we've got V squared over R squared. Now V is in both, so that is linked, and obviously if the velocity is a set amount at the bottom, it's a set amount at the bottom. So the only thing that can change the proportion between the linear and the rotational is the size of the inertia. That will change the proportion between the two. So if I is larger, more energy is used in rotation. If I is larger, more energy is used in rotation. And remember that I is linked to the mass and the radius, and we know mass and radius are the same. But I for the solid cylinder equals 1/2 mr squared, and I for the hoop equals mr squared. So assuming they're the same mass and the same radius, this is larger. And if that's a larger I, the hoop uses more energy in rotation. And if it's using more energy in rotation, the velocity at the bottom is less, therefore its acceleration is less. If you just think of the equations of motion, if Vf is less, the acceleration will be less, and that means it reaches the bottom later. And with the animation, which is based on reality, we can see that the hoop reaches the bottom later. So it's that proportion between the linear and the rotational energies, how it splits, depends on the size of I. So the proportion of the energies depends on the size of I. So that's something you need to remember as things are rotating. So if we just look to the next slide, it's the same picture, and I'm asking the question, which is the solid ball or the solid sphere? The yellow one or the blue one? The blue one, red one. The yellow one or the red one? Which is the solid sphere? And for those of you who want to look at it, why do they arrive at the bottom in the order that they do? And that's the end of the video.